Welcome, everyone. Yeah, it's a great pleasure to introduce our speaker today, Paul Goulart. So Paul and I met just a few hours ago, an hour ago, maybe. So all of his biography is from his website, but it's a really interesting biography, I think. I'll pick his brains afterwards. So I believe after you finished your undergraduate degree, you worked as a software developer and an engineer for a while, and then went back into academia doing a PhD at Cambridge in control, and then had positions at Imperial College London and ETH Zurich before joining the University of Oxford in 2014, where he was made a full professor in the last year. So I haven't met Paul before today, but I've very much known of his works and the good work he's done in high-speed optimization and control, and in particular in software for these things. And so, as everyone knows here, very dear to my heart is not just doing excellent research, but developing that in software that gets used in real-world applications. And Paul's an excellent example of there with software packages like OSQP, Clarabel, and Cosmo, and multiple other ones that he's been involved in, including some work. So, very interested to see what he has to talk about today. Over to you, Paul.
Okay, thank you. Right, thank you. So I'm, as you heard, I do a lot of numerical optimization, and I'm actually in a control group in engineering. So I do approximately 50% actual proper control theory, and then the rest of the time I do this. And we have a lot of problems which generally boil down to solve a convex optimization problem, and generally either a really big one or one that you want to solve really fast. So that's kind of what our motivation is. And so this talk will be about interior point optimization for conic quadratic programs. So by that I mean problems that have both conic constraints and quadratic objectives, but I want to keep the quadratic objective. I don't want to wish it away. And most of the talk will be based on work with UN, who is my PhD student, who's now at EPFL. And then the bit at the end where we get into the GPU stuff, that was in collaboration with Stephen Boyd and a couple of his students. So, okay, so I have always this slide at the beginning where I try to convince the audience that they should care about convex optimization. I gave this talk to Gurobi. They have Gurobi as an internal seminar, and I started to do it, and then I stopped. I thought probably you guys don't need to be convinced. But okay, I'll try anyway. So the interesting thing for this group is that we do some control stuff with Diamond, and so we did some stuff with high-speed projected gradient methods on the accelerator for controlling the beamline. But we have lots of different applications, and the pictures are all just things I happen to work on. So we do things on optimal power flow, building management, but then there's lots of applications in signal processing. I do a bit of machine learning stuff. Mathematical finance, we get a lot of users of our software in mathematical finance. You can tell they're in mathematical finance because you're the most aggressive about asking for free support for our software. And then it appears also indirectly, so as a subsolver in various applications. So we've done some stuff with Bayesian optimization. I actually started in numerical optimization trying to find stability certificates for fluid flow problems. How do you compute a Lyapunov function for a flow? We've done some stuff on combinatorial optimization and power electronics and so on. So in all of these cases, you want to solve your problem reliably, quickly, and you need some software to do it. And so what we've been working on for maybe 7 or 8 years is to make some software that is, sufficiently general purpose that it works in all the applications, but sufficiently reliable that people don't know anything about optimization should be able to use it, and it should just work. Okay, so we generally deal with problems of this type. Most convex problems, finite dimensional reasonable problems that people actually care about look like that. And so your problem is minimize a quadratic function subject to something that looks like an equality constraint, ax plus s is equal to b, and s is in some kind of cone. If the cone is the zero cone, then you just have ax equals b. If the cone is the non-negative orthant, you have a quadratic program, but you can do second order cone, semi-definite cone, you can do exponential cone, power cone, generalized power cone, relative entropy cone. There's all different kinds of cones, but mostly people care about the ones that are there. Most applications use even just probably the first 3 of the most common. And so we want to make a solver that does this well. And we had some first order packages that did this. OSQP does this for QPs in that form. Cosmo does it for general cone programs, but was written as a kind of prototype in Julia, and we always had this aspiration to turn it into something a bit more, let's say, user-friendly than something in Julia, which we might still get to. But during COVID, I was on sabbatical and I was stuck in my house, and Stephen Boyd wrote to me and said, hey, we should make an interior, actually said, hey, you should make an interior point solver that we can make as part of CVXPy, which is the kind of main Python modeling package, because the first order methods are not that accurate. So let's make a sort of high accuracy one to complement the medium accuracy one. And that's where this project came from. Okay, so let's talk about, yeah.
SN plus.
Oh, sorry, that's the set of symmetric positive definite matrices. Oh, okay. That's just my use of totally unnecessary notation that you won't see again. Will you? Maybe you'll see it again. Okay, so so initially I just wanted to make a kind of completely generic interior point solver, nothing fancy, just something free. And I kind of started off that way, but then we ended up maybe finding a slightly nicer way of doing it, which I would like to explain. So let's talk about how interior point methods work. Most interior point methods, they work like this. So you start with a primal problem, which is the sort of quadratic objective conically constrained problem on the left. And then you can write down its dual, which is the problem on the right. And how do most interior point solvers work? Like Mosaic works like this, the Gurobi barrier method works like this, ECOS works like this, lots of solvers work like this. First, you assume that the P is 0, and I'll explain why in a minute. Then you, or if it's not 0, what you do is you upper bound the quadratic term with some epigraphical scale or variable, and then you just minimize that variable in addition to the linear term that you had there before. And then once you've got a linear cost, then you can rewrite everything in what's called the homogeneous self-dual embedding, and then you try to find a feasible point for that. So let me show you what that looks like. So just get rid of that. Okay, let's just pretend that's not there. Maybe we can think that we've just baked it into the constraints. And if you drop that, what happens? So you can rewrite it like this as a feasibility problem. So you have here's just your primal constraints. This is your dual constraints. This one says that the duality gap is 0. This says that everything lives in the cone, and minimize 0 because you're just trying to find a feasible point. And well, so this one here is nice because everything is linear. That's the 0 duality gap term. And the reason why you want to drop that quadratic term is you kind of don't want to have a quadratic term in your equality constraint. That's one of the reasons why you drop it. Okay, so that's what we do. But then the problem with this is that if the problem is not both primal and dual feasible, then this will have no feasible points. Okay, so how do we fix that? Then what we can do is we just add two scalars. So we add this tau, which multiplies b, and we add this kappa, which acts like a sort of, I guess, kind of additional slack term to make up for the fact that you might not have 0 duality. And then you try to solve that instead. Okay, so now that's my problem. And so that's the homogeneous self-dual embedding. Why is it called that? One is that every constraint is homogeneous in the variable. So if you have a feasible point, you can scale everything and it remains a feasible point. It's always feasible, and it's the dual of itself. That's the self-dual part. Okay, great. And why is it always feasible? It's always feasible because one of two things will happen. Either the tau will come out to be non-zero and the kappa 0, and then you have a scaled version of the problem you want to solve, or the tau will be 0 and the kappa non-zero, and then it turns out that you have something like AX equals S, and that turns out to be a certificate of infeasibility for a problem, either a primal or a dual certificate of infeasibility. And so you either get a solution to the problem that you wanted, or you get a proof that no solution exists. And basically they you make a bunch of Farkas-Lemma type statements about whether or not the problem has a primal feasible or a dual feasible point or not. So you either get a certificate or you don't. Great. So And I can add this additional constraint here, which just says that that's just the condition that the duality gap is 0 again. Okay, so if I wanted to run an interior point method on this, what is an interior point method? It's a really fancy Newton method for this problem. Okay, so what I'm going to do is I'm going to set, I'm going to fix some initial variables. I'll get some residuals. Those are the terms on the right. And then instead of having this complementarity constraint, I set S and Z equal to the gradients of some barrier functions for each one of my cones. And then I just run Newton's method on that. So I pick a mu, I take a step, I reduce mu, I take another step, and so on. It's a bit, that's like how you would do it on paper. There's more secret sauce when you actually implement it, but that's roughly what you're doing. Okay, so let me now go back. And that's the problem that I started with. And I dropped all the red terms. So now what I want to do is just not do that. Okay, just keep everything in and see what happens. Someone was saying to me at lunch, it's, you know, the thing about engineers is they don't care about proving anything. That's exactly what it is, right? I'm just like, I don't care if this is, initially, I don't care if this is definitely going to work. I'm just going to try it. And it turns out that it works really well. So I'm just going to keep everything there and let me see what would happen. So what would happen is that your feasibility problem, this one here, which is the dual feasibility condition, that's not any harder. You just add an additional linear term. I've kept the tau and the kappa in there, but this one is a problem because you end up getting x transpose px, which is quadratic, and then divided by tau, which looks like awful, right? It's not something that looks particularly appealing, but okay, I'm hopeful, optimistic, let's say. So let's just try it anyway and see what happens. So that's my system that I want to find a 0 for. You can prove that it's still always feasible. If your problem is, if your initial problem is infeasible, then you can always find a non-zero kappa and produce an infeasibility certificate. And if it's actually feasible, then the kappa will go to 0, the tau will be non-zero. You can scale everything up to get a solution to the problem that you started with. And every positive scaling of a solution is a solution. So that's homogeneous. It's not self-dual, but the self-duality is not really that important for proving, well, okay, maybe for proving convergence it's important, or helpful anyway, but for implementation, it doesn't make any difference if it's self-dual or not. So I get basically all of the same guarantees about infeasibility certificates or feasibility of the whole problem, but maybe I should worry about what it would mean to take a Newton-like step for a system that looks like this, because I have this 1 over tau x transpose px term working. So, okay, so let's just have a look. What does it look like to take a Newton step for this system? I fix the mu, and I just try to make a Newton-like step. So I get a system of equations that looks like that at every iteration. And what's the difference between that and what I get if I had the homogeneous self-dual embedding? The bottom right-hand corner appears as a non-zero term, and the bottom left-hand corner is modified by some linear term, actually x over tau term, and the p appears in the corner. But everything else is identical. So I can take a standard HSD solver and just basically take the linear system that I'm solving at every term and just inject a couple of additional pieces into it and go. And so I have here 5 variables, s, kappa on the left, x, z, tau on the right. And when you solve this system, what you do is you eliminate some of the terms and you try to condense it down either to a positive definite form or at least a symmetric form. So we do it at the moment in the symmetric form. So we reduce it down to this 2x2 system. And the only difference between that and what you get in the sort of linear cone case is that the right-hand terms are a little bit different and you get a p in the corner. Okay, so why is this, by the way, how do I know that I'll be able to factor that? So what I do is I shift the p by some sigma I, for some small sigma. And the h is going to be negative, well, the minus h will be negative definite by itself. So the system is quasi-definite. And so I can prefactor it. I don't have to worry about pivoting or anything, as long as I'm not too scared of like close to 0 pivots. And so I can find a symbolic factorization for this and just reuse it at every step. And that's kind of the same thing that happened in our ADMM solve. We end up with a quasi-definite system, which you can symbolically factor. It looks exactly the same.
In the system, this H is non-self-adjoint, right?
It's
The H is non-symmetric, right?
no, it's symmetric. It's symmetric. Symmetric, yeah, yeah. So and it's definite. So okay, so and the reason I left a lot of details out is because we use the Nesterov-Todd scaling, and you end up the H is some W transpose W for some scaling thing W. Okay, so why is that better than
The
what I
ds and the dk kappa and the d tau have disappeared from.
They've all been. That's what the tildes are doing a lot of work for me.
Okay.
What I want to say is about the left hand side, because I want to show you what would have happened if I had not kept this quadratic term there. So what happens is that if I had set out to force the problem into one with a linear objective, then what I would have to do is I would have to take the quadratic term in the objective, I would upper bound it by something. So I would have some x transpose px less than some scalar. That's a quadratic inequality. I want to put it into some standard cone form. So I factor the p and get a second order cone constraint, which is now a constraint. And so what happens is that you get something that looks like that instead. You get this additional term, which is the square root of p. And you get this additional cone, this additional term, which is from the barrier function of the additional second order cone constraint that you added. And so you have a system that is bigger. You factored p. If p is not diagonal, then maybe you've got a lot of fill in the p. And then you factor it again, and you get even more fill in. So two things happen. The first thing that happens is that you get a bigger system, which generally has a lot more non-zeros in it. And the second, which, okay, that's easy to explain. The second thing that happens, which is not so easy to explain, which I actually don't have a good explanation for, is that if you do it the way on the left, it takes often far fewer iterations than if you do it the way on the right. And okay, that's where I get to the, I don't care why that works. That works. We'll leave it to someone else to figure out why it works. Actually, okay, we'll figure out eventually why it works, but for now, we're happy that it's faster. Okay, so that's our basic method. We just implemented that. There's no other tricks. Everything else is standard looking interior point methods. Okay, so I said a bit of stuff at the top. So we use direct LDL factorization for the left-hand side. We do some sort of standard equilibration stuff. That embedding is used also in ADMM, in the SCS solver. They use a very similar trick now. NT scaling, all the standard stuff. The only difference is the treatment of the quadratic. Okay, so what about sparsity? What can we do with exploiting sparsity in control? So yeah, so okay, so I have this. This is the system that I want to solve. If it's sparse, that's great, and I've not factored the p. But maybe I should worry about also what's happening with the H. Okay, how can I make H remain sparse? So what happens with that term there? So if I have a second order cone constraint, then in general, the H matrix, so my cone can be a composition of cones that look like this, but I'll just think about them one. So suppose I just have one second order cone constraint. Then the H matrix is a dense block that fits into my matrix there. And so if I have a very big second order cone constraint, I'll have this great big brick of non-zeros. But it turns out that that matrix is actually diagonal plus two rank 1 updates. And you can compute what the U and the V are based on the barrier function for this cone. And so instead of solving a system like the one at the top left, you can just expand it a little bit and you can solve a system that looks like that. And now D is diagonal and V and U are two dense columns. And now the system is a lot sparser. So what we do is we take, if the cone is like dimension, I think 5 or less, we keep it as a dense brick. It's more than 5, we expand it. Why 5? Because I tried loads of problems and 5 was the point where it didn't make a difference. So, okay, that idea is what is in the eco solver, but then we did some stuff, are there other cones where you can do this? So there's other cones, we have this generalized power cone, which is like a kind of, if you take all the alphas to be equal, then you get a constraint on the geometric mean of something. And so can I do something similar with that? Well, it turns out you can. That big H, which could be a giant dense matrix, is a diagonal plus 3 rank 1 updates. And so, okay, we can do that, and then we do that. Great. And then it's sparse again. And we can do that with a couple of other different types of cones. So the first thing that we can do to exploit sparsity is to just, for certain conic constraints, we can just enlarge the linear system very slightly and expose these rank 1 update terms. That's a relatively small thing that you can do. But what about semi-definite programs? Can we do something with semi-definite programs? So with that, that's a slightly more involved problem. So let's just talk about what happens there. So in a semi-definite program, I would have the H matrix. If I have a single constraint on a matrix, then it should be semi-definite. Then H will be something, if that matrix is n by n, that has to be positive definite, H will be something like n square by n square, or maybe n over 2 square, but really big is the point. And that's bad. So what I would like to do is I would like to take one great big semi-definite constraint, and if I can, split it into a bunch of smaller semi-definite constraints. So there's a nice trick to doing this, and it's based on what's called chordal decomposition. So let's suppose I have a matrix like the one on the bottom left that has to be positive definite. Generally, when you get a constraint like that, it has a bunch of terms which are allowed to be 0, or maybe required to be 0. And I can think of the pattern of non-zeros there on the bottom left as corresponding to some graph. Okay, so then what I can do is I can compute the maximal cliques for this this matrix, and I get something that looks a bit like that. So I get all of these dense bricks that overlap, and if I think of it in terms of graph, each brick looks like a clique. And now I can use this really nice result that says that if a matrix is sparse with a bunch of cliques that I identify, then the whole matrix is positive definite if and only if I can find semi-definite components that add up to S and which are all individually semi-definite. And so why is that good? It's good because now I have a constraint that says that green, blue, and red are individually semi-definite, and they satisfy some additional equalities rather than the whole great big thing being semi-definite. And since the terms in my KKT system are scaling like the square of the edge dimension of all of these things, that makes a massive reduction in the size of the problem that I want to solve. Okay, so that's a known thing. Now I'll show you a bit of a problem with that. So if I have some cliques like this, if they're partially overlapping, like in the top left, maybe just by one element, then it makes sense to break them up into a bunch of individual 3x3 matrices. If they're overlapping almost entirely, just with one piece missing on the corner, then probably you don't want to make a green and a red semi-definite matrix. You'd rather just have one of size n+1. That would be probably better. So what can we do? So in the left, you actually want to split them up. On the right, you want to merge them together. And we want some smart way to merge them together. And so we started to work on this clique merging idea. So I have some sparsity pattern, like on the top left, and I make some graph out of all the different cliques on the right. And then I can get some clique tree. This is actually computed, like when you factor a matrix, you do some symbolic factorization, you actually get all of this for free. So I get some clique, which is the yellow one, and that's this sort of dense subset on the top left, where it's this collection of cliques on the right. And then I just work my way through this graph. So I get the green one, which is some other clique. It corresponds to a different brick in the top left, or a different group on my graph on the top right. And I just keep working through the tree like that. Okay, there's the red one, there's the blue one, and so on. So what do people do with this? So they form the clique tree, and then we say, I would like to merge some of these cliques into a bigger clique, a bigger block. Which one should I pick? So I form this tree, and then I can't just pick any two and merge them together. I'll break things if I do that, because it won't be a chordal decomposition anymore. So, but what I can do is I can maybe choose parent-child relations. I can maybe merge the green and the red, or I can merge siblings. I can merge the green and the blue. And if I do that, both of those things are legal in the sense that I won't break the fact that the thing is still a chordal decomposition. And I can come up with all kinds of heuristic metrics about how to do this. So the problem with that is that when you make the slides, you can choose the clique tree in the most disadvantageous way possible. And in my tree, the right thing to merge is really the top left. I really want to merge the thing on the top left, because if those are almost entirely overlapping minus two terms. And I just want to make that into one lumped bigger matrix. But the problem is that the red and the blue are not parent-child, and they're not siblings. They're like uncle, nephew, or aunt, niece, or something. And so none of these methods will work for that. And it's an accident of the fact that that's the clique tree I got, because there's not a unique representation of this tree. There's two others. And there's ways to write it so that red and blue are siblings, and there's ways to write it so that they're parent-child, but it's not obvious which one I'm going to get. And it would appear to be legal only for the left and the right, but not the one in the middle. Okay, so that's kind of a problem. So we just do a different way. So we use instead what's called the reduced clique graph. And what's that? It's basically the union of all the edges that appear in all possible clique trees. You can compute this easily. And you get, now for us in this small example, it's a fully connected graph, which actually tells you that you can merge any two that you want. That doesn't always happen, but you get this nicer graph. And then I can compare, what does it mean to merge any two things on this reduced graph? And so what we do is we just look at all the edges. And I say, okay, I'm going to look at every edge, and I'm going to compute a weight. What's the weight? It's the cardinality of each clique cubed, because I think that the cost of factoring a matrix will be proportional to the cube if I were doing, say, ADMM. And then the cost of factoring the other one cubed minus the cost of factoring the union. And so if that number is positive, that tells me that probably I should stick them together. Okay, so we do that. We merge them when they have a positive weight. And then I consolidate, I fix up all the edges, and I just keep doing that until it doesn't seem like a good idea to merge them together anymore. And what happens is that you start with this great big sparse matrix, you break it up into all of these cliques, and then you just selectively merge a bunch of them together until you get what appears to be the best, or at least a reasonably good combination. It's not optimal, because it might be that there was some choice of 3 cliques that I should have or something, but it's reasonable and it's fast. It's fast. All of this is a kind of pre-processing step. It should be not more than 1% of the total computation, and it is. Okay, so we implemented that as well. Actually, we implemented that in the Cosmo solver. And now I started to try to put all of this stuff together into a name. And this is called Clarabel. Why is it called Clarabel? Because my children are called Clara and Mabel, and I told them that they were allowed to choose the name, and they argued about it for ages, and then they decided that it would be named after themselves. And Mabel is really angry that she thinks that Clara got 5 letters, and she only got 3. I tried to tell her no, the A. It's okay. I should have put a line or something. Okay, so right, so we made this interior point solver. And we did it in sort of 2 phases. One is we made first a Julia package for prototyping. And then once that was done, we made a Rust port. And okay, there's lots of reasons for doing that, which maybe I'll come into, but it's the point for the moment is it's all open source at the moment. You can, in Julia, you can just install it through the regular package manager. In Rust, you can just go to crates.io, which is where all the Rust stuff is. It also has a Python interface. It also has an interface in CVXPy. So if you use CVXPy, this is now one of the defaults in CVXPy. So actually, CVXPy has 3 default solvers. One is OSQP, which is our QP solver. One is this, and one is SCS. So we get about 3 or 4 million downloads a month, just by virtue of being the default within this ecosystem. That doesn't mean 4 million people. Could mean 10 bots, each doing it 400,000 times, but it's a lot of, so we get a lot of users. Okay, so I wanted to make this, the fact that we have these two implementations, we want to make it as user-friendly as possible. So here's an example problem. So I have just a QP with left and right constraints and an equality. And so first you just write it in the standard form, or CVXPy will do this for you. And now I have quadratic cost with AX less than B, or AX equals B. So I have 1 0 cone constraint and 4 non-negative cone constraints. And so in Julia, you can just basically write down your problem. You write down your list of cones. It doesn't matter what order they're in. You give it some default settings. You say, make a solver, solve, gives you the answer. And what I wanted to do, and this has also a jump interface as well, but this is just the direct interface. So then what we wanted to do was to make this experience as close as identical as you can in all of these languages. So that's the Julia version. That's the Rust version. It's almost the same. P, Q, A, list of cones, settings, make a solver, go. Looks almost the same. And also in Python, looks basically the same. And this is nice because sometimes people ask, like, isn't it a pain to have two identical versions of the software running? And the answer is not really, because if I look at the Rust and Julia, I mean, they look almost the same, and internally they look almost the same also. So I give, if I have a PhD student working on something, they make a modification in Julia. It's usually a mess. I clean it up a little bit. Okay, now we're happy with the Julia version. We release that. Maybe this takes 2 or 3 months of work for us to make some modification, but then to port it into Rust is always 3-4 hours of copy paste, put a bunch of ampersands in strategic places, add a couple of packages, and it just works. And Rust is a really, really nice language to write code in because it's very opinionated compiler. Stops you from doing anything really stupid. So I've had a good sort of experience with that. So that's our process. So we write everything in Julia, we port it to Rust, we have C and C++ wrappers, and then we have some, there's a MATLAB interface, I think some third-party group made for it. Drake and Toyota, which is some robotics package, uses it. Then we have a Python wrapper, which goes through Py03, and then we have the CVXPy wrapper. So, there's 2 actual implementations, but we support 4 or 5 different languages. Also R, support, and so on. Okay, so this is really nice, and everything translates really easily, and I will just make an observation. This is a really nice way of going about things. Why? Because Julia is really nice when your algorithm goes wrong. Why does my algorithm not work? Because there's a negative eigenvalue somewhere. I can just, in the terminal, just plot stuff, look at eigenvalues, do a SPI, all this, and that's nice for mathematical issues. But then Rust is much nicer because the compiler is so opinionated. It doesn't let you do stuff that's probably ill-advised, which is annoying in the moment, but it stops you from making bad design decisions. And occasionally what will happen is we realize it's not possible to implement something a certain way in Rust. And pretty much always our conclusion is, yeah, we probably shouldn't actually do it that way. And then the Julia code gets modified instead. And it doesn't really take that much extra time. And in terms of performance, they're very close. Julia is really, really close to the performance that you get in C, as long as you're careful about allocations and so on. Okay, so let me show you a bit about solver performance. So we have about a couple of thousand, 2,000 or 3,000 different example problems that we got from all different open source repositories. And we try them on R solver in Julia, R solver in Rust, Mosaic, Herobi, Ecos, a couple of other ones. What are they? Highs, and then any others that seem reasonable. And then you form these performance profiles, which probably you've seen before. So I gave a bunch of problems, and ideally what I want is for my version to be as far up and to the left as possible, because if you pick any point, like this one here, the green one there, that says that for 60% of the problems, the green one is within a factor of 2 of whatever happened to be the best performing solver on each of those problems individually. So ideally, you go straight up and then straight across, which means that 100% of the time you're the best. So, okay, so for QPs, this turns out to be the fastest way against all of these other solvers. And oh, I should say I disabled pre-solve for Gurobi and Mosaic because Gurobi will occasionally pre-solve your problem on you and not actually do anything. So this is not to say that we are actually the best always. I'm trying to say that this method is better than the Gurobi barrier method. And it's especially good when you have quadratic objectives because that's the only time it's really any different. So for these model predictive control problems or like finite horizon optimal control problems, the Julia one is quite substantially fast. Sorry, the Rust one, which is the red one, is quite substantially faster than all the others. The Julia one is pretty close. The only reason for the gap is basically that there's a little bit of setup overhead when you create the settings and so on, but the actual core performance is roughly the same. And the others are lagging a little bit. And then I can do it also for time. It's a little bit clearer to see that the Rust and the Julia are close in this time. So this is what fraction of the problems did I solve within a certain amount of time is the x-axis. So you can see there's a little bit of gap down at the very, very fast problems between the Julia and the Rust. There's some non-zero setup time difference between the two, but then they're more or less agreeing all the way up to the top. And the others not so good. And then we can form other types of QPs. So we took a bunch of matrices from the sweet sparse library, and we try to solve sort of regularized AX equals B type problems to these, either with adding a Huber penalty or a sort of lasso regularization term, just to make up a bunch of QPs that were big and which had sparsity that was representative of problems that seem like real problems. I don't want to just randomly generate problems because then all the problems will be nice and that's not really fair. So here you can see a bit of a difference between the red and the blue there. Why? It's because, so the green one is Gurobi. Why is there such a big difference between the Rust performance and the Julia one for these problems? It's because in Julia, the LDL factorization code is just our own simplicial LDL factorization code. Whereas in Rust, it's slightly fancier than that. What happens is that we symbolically factor matrix that we want to factor it every time. And if the ratio of non-zeros in the factors to non-zeros in the data is sufficiently high, then we switch to a supernodal method. And so that gap is basically the gap that you get from the extra performance of dynamically choosing a good solver rather than just picking one. I should say we do support other linear solvers. We support in Julia MA57, Paradiso, MKL, another Rust supernodal method, CUDA, and so on. So we have, and it's easy to drop in nuance if you want. But that gap is basically the difference between MKL and a simplicial method for the bigger problems. And what about LPs? So for LPs, then what happens is that the performance is basically roughly the same as everybody else, except for the optimal power flow problems, which I don't really understand. And Gurobi was sort of mad at me when I showed that we were faster than them, and they said I was doing it wrong, but I don't think I was really doing it wrong. I don't understand what was going on, but I did rerun it, and that is like, I keep getting the same picture, which they did not like, but yeah, maybe they just have, bad choice of factorization. Probably there's some setting I could switch to get it to agree, but this is just straight out of the box. Okay, now that's all on CPU. What about GPU? So we then decided, let's see if we can get this to run on a GPU. And how fast could we make it go? And there's kind of three basic pieces that need to be replaced. You've got all the easy stuff that you can parallelize. So Julia is very nice for this. It has, it's all based on kind of type abstractions in Julia. So you can just replace the standard vector type in Julia with a GPU-backed, device-backed vector, and then everything still just works. But In Rust, you have to do it yourself, but fine. So we've got the basic parallel operations. Then we've got a bunch of operations over the cones. So I might have a long list of 1 million second order cones that I need to perform barrier calculations on, so on, which we need to deal with. And then we've got the linear system solve. So those are the 3 pieces to fix. The first one is easy. The middle one is kind of annoying because what we realized was that we had this array of structures, one structure for each cone. And really probably what you need is a structure of arrays so that you can easily vectorize all the operations on them. So we did that in Julia. There's no Rust version of this GPU solver yet, but in Julia we have it. And it just required some hassle for load balancing across the second order cones and parallelizing by the cone types. So load balancing means that if you have a bunch of really big second order cones, it's better to add a lot of variables and end up with lots of small second order cones so that you can parallelize over the cones. Okay, we did that. And then what about the linear system part? Well, we just use CUDA because CUDA has this, NVIDIA has this CUDSS, direct sparse factorization code. And the experience so far is that the fact the symbolic factorization time is bigger, a lot bigger, but then the per iteration times are much faster. And maybe there's some way to fix this, but at the moment, that's where we are. And we started to then, you can experiment a little bit. So what about mixed precision solves? So what if we, what if in, on the GPU, we factor our matrix 32-bit, but then once we've factored it, we do a kind of iterative refinement to solve, and we can do the iterative refinement in 64-bit. And would that be faster? Just try it. Okay, so we tried that. I'll show you a bit about that in a moment. So how do we do then with second order cone forms? It's always fastest by a lot. Much faster than the CPU version. It's even more robust than the CPU version, which I don't understand why that is. And then if I have Mosaic, even if I allow Mosaic to have pre-solving enabled, which I don't have, I have no pre-solve. Well, okay, anything that's an infinite upper bound, we drop. That's our pre-solve, is drop constraints that are infinite. We still do a lot better than Mosaic. And if I turn Mosaic's pre-solve off, then it completely fails. And it's only solving 10% of the problems because it's hitting the time limit, not because it can't solve them. And so this is for cases with, from the pglib optimal power flow library, problems with more than 2,000 cones, so relatively big problems. And then what about the 32-bit stuff? Okay, so we tried a bunch of portfolio optimization problems and Huber fitting problems and so on. And we just checked how many iterations does it take and what's the time if I do the internal solve 32-bit or the internal solve 64-bit. And the number of iterations more or less doesn't move, maybe +1 in a few places, +4 on the third one, but the overall time goes down a lot. Partly the reason why the overall time has gone down a lot is because we're solving it on basically a commercial grade gaming graphics card, a 4090 GPU. So it probably the number of 64-bit operations is limited on that device. So you probably wouldn't get this kind of performance if you spent 30,000 pounds on a nicer GPU. But okay, my budget did not extend to that. So the point is more that it works, and it doesn't really seem to hurt you, at least in terms of the iterations, and maybe it's a bit faster. Okay, so now you want to say, that's amazing. Where do I get all that? So if you go to clarabel.org, you can just get all the documentation, and there's a bunch of examples and so on. And then if you just put name of language in front, so julia.clarabel.org takes you to the Julia GitHub site, or you can just download it from the package manager. In Rust, you can get it from crates.io, and it also has its own Rust-specific documentation. Python, pip install Clarabel will work. C++ and R, it's all there. And we try to make it so that, and we do this with OSQP as well. We kind of feel like when you install it, if it takes more than one line to install it, then people won't use it. So none of this, there's no CMake, there's none of this. You should just type one thing and it should work. And all of these, not C++, okay, but the others, it just works just with one line. And it works, and it works on, basically any reasonable platform. That's really big to get. Well, it also reduces the number of people emailing you for instructions. But you get a lot of users just by making it as easy as possible. Okay, so with that, I will stop, and I'm very happy to answer questions.
Questions?
Regarding the chordal property, like
Yeah.
isn't the theory like the cliques needs to be of size less than 4?
Yeah, you can say that. Yeah, there's a fully connected graph of 3 that's a clique. If you have 4, then you have to put a piece across the if you have 4 that are connected in a square in the diagonal, then you have to add 1 across the other diagonal to make it into a clique. So it has to be it's a fully connected subset. Yes,
Yeah,
that's true.
But to have the decomposition as a sum of
Oh, I see what you mean. Yeah. So okay. So what you can do is if you don't have it, so there's not every graph has a chordal decomposition like that.
Right.
But it's fine to I mean, what is it that I'm finding? What is the graph? It's the set of points for which a non-zero might exist. So what I can do is I can add an edge to make the graph chordal, right? Allowing a 0 to be treated as a non-zero for the purposes of the partitioning. But then I still have a constraint that says that it's 0. That's fine. I mean, I fill in a bunch of edges. And when you do, if you do a symbolic factor, so what we do is we form the symmetric matrix, we do a symbolic factorization with AMD, and then you just get the chordal decomposition or the chordal completion and its decomposition directly from the symbolic factorization.
We have a question online. Are there plans to expose the Rust API on Julia?
Yes, because it's exposed already. So it's not documented because it's only really there. It's mostly there for me to be able to do the benchmark. So the benchmarking is all in Julia. So we have this benchmarking file array that runs all the different solvers. But in the Rust code base, 4 or 5 levels down, there's a Julia interface, and you can compile the Julia interface of the Rust version and use it in Julia. That works fine. I use that all the time. The only reason why we don't advertise it is because then it would be, I think it would be confusing somehow to users to say you can use it in Julia with the Julia version, or you can use this other identical version in a different language, also in that first language. And by the way, the performance difference is 0. It would be very confusing. But for testing, for sure, we do that, and it's all public.
Paul, I don't know if you can hear me. It's Nick Gould here. I'm remote. One thing you haven't really said very much about, which I'm slightly concerned about, is that notoriously interior point methods produce worsening condition matrices as you converge towards the solution. So
yeah,
do you see that here?
Oh, for sure. I mean, well, you definitely see that the conditioning gets really bad.
And
for QPs and LPs, it doesn't matter. Well, okay, what do I mean it doesn't matter? What I mean is that when we try to solve LPs and QPs, they don't usually fail because of poor conditioning. They might fail because of very bad data scaling, but I don't think it's the condition number of the KKT system that you're trying to factor that is the issue.
Sorry, can I just come back on that?
Yeah.
There are basically 2 sorts of QP problems. There are those that are non-degenerate, and then there's the ones which are degenerate. But degenerate ones, you need much more accurate solutions because the variables will only be converging at the square root of the barrier parameter. So typically, if you want 12 figures, you're going to need your barrier parameter to be 10 to the minus 24, and that's going to be pretty tough. So what do you do about that?
Well, nothing directly. I mean, I can tell you that what we do is I showed you the quasi-definite system that we solve. We shift the upper left and the lower right by some epsilon I to force it to be at least actually quasi-definite instead of semi-definite. We factor and solve. When we, at least for our own internal factorization, we remember what the sign of all the pivots should be. If we hit one that's too close to 0, we just artificially force it away from 0. I mean, this is a completely hack-tastic way of doing it, but okay, that's what we do. And then we get some solution, and then we do some a couple of rounds of iterative refinement on the solution that we get to try to get rid of the shift. And that works. I mean, what we found is that works in practice basically all of the time. We don't do anything special about it other than that.
Okay.
The bigger problem is that for the second order cone problems suffer from ill conditioning seemingly much more often, and it's because I showed that we have that sort of sparsification procedure, and so we do that. We do something like that, and the U and the V can start to become sort of collinear and weirdly scaled when you get coastal optimality. And I don't really have a good answer about what to do with that. So those ones, you've got a much greater chance of only converging to about 10 to the minus 6 or 7 when you solve great big second order cone problems that way. And yeah, I don't have a good answer for that. Although one thing I'll say is that, so when we solve a system like the one at the top, we do then iterative refinement there, but I actually think that's wrong. I think what we should do is we should go back to there. We should solve it. We should reassemble a solution to the upper system of equations, compute residuals, and then do refinement that way. That seems to help a bit sometimes, but it's not implemented because it didn't help often enough, and sometimes made it worse. So we left it out for them. But it's kind of an issue. But in practice, well, let's say no one's complaining about it for the most part, so we're not excessively worried about it. The people who do the second order cone problems generally are actually happy to terminate it about 5 or 6, that 10 to the minus 5 or 6 relative accuracy, and then there's any real sets of problems where that doesn't work.
Okay, so some of the commercial solvers, of course, have they have post-optimality crossover, so that you actually get an exact, in some sense, exact solution. Do you do anything like that?
I know that, well, they do it for LPs. I don't know that they do it for second order cone programs. Perhaps they do. We don't do anything like that. I know that in our ADMM solver, we do have a kind of polishing step where we'll solve to 10 to the minus 5 or 6. Then we look at the what appear to be the active constraints, set them to be equalities, have one try of solving them as if they were actually equalities. And if that works, then we hand that over as the solution. Otherwise, we just say, here's what we got. And I know that there's some stuff by Stephen Boyd's group on, let's say, whatever is the polishing equivalent of a second order cone or a semi-definite constraint, but we never tried implementing any of that. I mean, it would be nice to do that, but yeah, it would be nice, but this is like a nights and weekends kind of endeavor. So yeah, so no.
Thank you.
Turn on mute and ask a question.
Yeah, I mean, Ian Duff here. Yeah, I very much enjoyed the talk. One question on your linear solvers. You mentioned, and you showed an example, dramatic example, where you benefited a lot by checking in the analysis how much the fill-in was, how much non-zeros and the factors essentially, I guess, what you're doing, and then you switch to supernodal or multifrontal if it's filling in a lot, which is great. That's a good thing to do. But I have two questions. If you can ask them. 2 questions. One is, what are you doing when you don't use supernodal? And the second question is, the problem is that when you do the analysis, you're not including normally any numerical factorization. And the numerical factorization, Nick just referred to that, when you've got nasty problems, is going to click in, and you're going to end up with many more factors and non-zeros in the factors than you got from the analysis. So maybe you should be switching to supernodal more often, or maybe you should be using supernodal all the time.
Okay, right. So so the first bit was, what do we use when we're not using the supernodal? There's a package from Tim Davis, which is sorry, can you hear me or no?
Yeah, sorry, yeah.
So there's a sort of, let's say, like a tutorial grade Koleski factorization from Tim Davis, which is computing LDL factorization without, which just does symbolic factorization without, worrying about the values. And we just basically use that. I coded it directly out of the paper. We didn't use his code because of licensing problems. So it's just that. It's like the simplest possible LDL code you could have. Otherwise, we switch to the supernodal method. The reason why we do not, so to be clear, when we do LDL, we do not do any of this kind of, what is it called? Bunch.
Not doing pivoting.
Yeah, we're not doing any pivoting, and the D matrix doesn't have any 2x2 blocks. It's just LDL. And so when we factor, we shift everything away so that it will definitely be at least in exact arithmetic quasi-definite. And so then you only care about the symbolic pattern of L. And so the reason why it fails sometimes is because, it's not exact arithmetic. And so you probably should be doing some pivoting, but we don't do that. I mean, we could, it wouldn't be difficult for us to add an additional linear solver, which does do pivoting. That's fine. But we just haven't done that yet. And it's partly because, we try to keep everything Apache licensed. And they're just, the kind of landscape of extremely free linear solvers is not amazing. And I don't want to write it myself. So we have what we have.
Yeah, most of the solvers you use have got pivoting anyway, but yeah. Okay, I'll have to pass you back to Nick then about the pivoting side and whether you need it, but there we are. Thank you.
I think there's one online.
Cora, you unmute yourself.
Hello, thank you for the nice talk.
Hi.
I want to ask, what about instead of Newton's method, using some first order method because of the need for more scalability? So for example, especially for semi-definite programming, do you find that maybe it's too much to be doing all this, and one should be one should be doing less?
That's a different talk. You can, if you invite me, I'll come and give you that talk instead. So we have also an ADMM QP solver, and then we have this thing called Cosmo, which is an ADMM cone solver. And recently we tried to sort of hybridize them to make a kind of half ADMM, half interior point solver with partial success. Because what you can do is you can make a kind of interior point step. And then you get this KKT system, which is factored, but then that is exactly the same as what you would have with ADMM if you had just the right kind of regularization penalty. And so what we can do is we can make our interior point step, usually do like a predictor and a corrector direction. But then if you want, you can take a couple of extra ADMM-like iterations to try to get closer to the central path. And then once you seem to have run out of steam there, you stop and then you do another interior point iteration. Or alternatively, you can do something that looks like ADMM, but with the barrier parameter behaving kind of like it were interior point. Or we've also done some stuff where we make an interior point initial, we try to compute an initial point, and then we try to fix it up with ADMM by trying to get closer to the central path. And then from there, we continue with interior point. So yeah, eventually what my aspiration is that I wrote all of the code so that all the bits are sufficiently mix and match that it should be quite easy for me to now make an ADMM solver or maybe a PDHG solver out of the parts that we have. And then that would just become an extra option in the solver. And you can say which method you want to, an ADMM, PDHG, or interior point, and it should all work through the same interface.
Okay.
One day.
But the ADMM or the extra gradient is different. It's not on the interior point system. It's not on the.
No,
It's
that's
not
right,
on the.
but-
It's not. So they are still separate. They are still. The interior
the moment,
point is
yeah,
with factorization is completely separate than these other ones.
They're two completely different codes at the moment, but the components that you need to make an ADMM solver are not different from what we have already. I mean, the only thing that we would have to add is projection methods for all of the cones, and then just assemble, some high-level ADMM solver. I'm
Great.
fairly confident.
Thank you very much. Yeah, thank you. Thanks.
Sorry, more of a basic practical question. So, I mean, your first slide talked about controls and optimization. So I didn't quite get the bridge of how you would sort of go from what you presented to sort of real-time control systems, or how do you, given the sort of Julia, Rust, where's the sort of performance gap, or how do you implement on FPGAs, or is there how does it translate to real time?
Do not implement on FPGAs. So if you wanted to run it on a real-time system, so generally if people are running on real-time systems for some robotics application, it's generally a QP. And most of those people use our ADMM solver because it's just in C. It's even in C89, right? So, I mean, it's crazy. It's C89. But so that package is completely library free. The Rust version, if you don't compile it with any fancy, semi-definite programming features or anything, is very nearly library free, aside from a bunch of macros. But it's not allocation free. So I would be maybe a little bit reluctant to say that I could run the interior point solver on a robotic system, but I'm quite confident that you could run the ADMM QP solver on a robotic system, because as long as you actually there's a whole bunch of other stuff that we've done on code generation. So what you can do is you can pose your optimal control problem. You can symbolically factor everything ahead of time for ADMM, because you only need to factor one matrix then. Then you just dump all of the factors into a automatically generated header. And then when you run your solver, there's no internal allocations at all. Everything is statically allocated from the beginning, and you just run solve. So yeah, there's lots of people in the robotics community and flying little drones and things that use the QP solver. And I will eventually try to make the Rust version also not use any standard library components and make it so that you can give it a custom allocator. But it's a nights and weekends project, so probably that's going to be a while. Right? Or someone will contact me and say, I'll pay you to do that, and then I'll simply do it faster than I do.
Any other questions? I know we're over time a bit. Well, we should probably leave it there. Thank you very much, Paul.